talk about electrolysis. We've got some excited students here today. Uh, it is nearly spring break, so anyway, I know what you mean. I didn't spell that right. I did. Electrolysi. That's multiple different electrolysis. Okay, so we were just mentioning that there are certain metals on the periodic table, like for instance sodium or potassium, or even calcium and magnesium, that are highly reactive. So reactive, in fact, that if you leave some sodium out, it nearly instantly corrodes just by being in contact with the air. So what that means is, unlike with less reactive metals like, say, platinum or gold, which don't tend to react at all, okay, um, these are very hard to obtain from nature, right? You have to use advanced techniques in order to get them. So ancient people knew about things like platinum and gold because if you have some, stone that happens to contain, a vein or a nugget of gold, and you threw this in fire, basically the gold would just like melt out of it, and you could collect it. I'm sure this is a little bit simplified, but I'm sure, very early on in human history, walking around on the ground, you might see a rock with a hunk of gold in it, right? And you might throw that on a fire and out it would come. So from, the days of ancient Egypt and even earlier than that, there was stuff made out of gold, right? Gold is unreactive, it's easy to get. You do not find sodium, potassium, calcium, or magnesium because, first of all, ancient people probably didn't know they even existed. Second of all, in order to get them, you have to do some special stuff. So let's just focus on sodium because it's very common. Okay, so where in nature is a very common place that sodium hangs out? Where do we find a lot of sodium? Yes, good. Sodium chloride. So our oceans are filled with sodium chloride and other salts, and the tables in our houses tend to contain sodium chloride. It's very, very common in nature, right? And it's made of two highly reactive chemicals. Sodium is highly reactive, chlorine is highly reactive, okay? What if we want to get some sodium for whatever purposes we might have for it? Well, you can't just like melt this stuff. It doesn't decompose. So what you have to do is you have to create an electrolytic cell. And this is going to be a pretty gnarly scenario here because what you're going to have to do is you're going to have to create some sort of crucible or container, okay? And you're going to have to put your salt crystals in here. And then you're going to have to heat them to an extremely high temperature. So let's see, how do we make it look like it's hot? So we need like some sort of like heat source that's very high heat. So this is my fire here. So maybe like some sort of like, no, this isn't a hand. This is like a gas burner of some sort, okay? And so what this will do is it will melt sodium chloride. First of all, can sodium chloride in its crystalline form pass electricity through it? Can electricity move through sodium chloride crystals? No. Ionic compounds are locked together. You cannot pass ions through it. However, if this were molten, if it's melted, you're actually breaking up the crystal structure. And now what you're doing is you've got this chamber containing free-flowing, free-moving ions, right? So once it's liquefied, you've got this scenario. Now it's become an electrolyte, okay? Now it's ready to have electrolysis done to it. So what are we going to do? We're going to get some sort of they've got to be pretty robust electrodes, right? And we got to fire them in here. I think it's often done with carbon or graphite electrodes, but don't quote me on that. We can look it up in a bit. And then what you're going to do is you're going to actually attach a power supply to this, okay? So you're going to make these positive and make these negative, and then what will happen is over here, we're going to have sodium attracted, right? So this is attracting cations. So in this scenario, is this a cathode or an anode? Okay, and at the cathode, sodium is reduced to sodium metal. So electrons here are essentially forced this way through the circuit, right? I hope I said that right. Okay, and when the sodium gets here, right, it's reduced to sodium metal, and how they collect it at this point, I'm not exactly sure. And over here, you're going to have lots of fun because what's going to happen is these chloride ions are going to drop off electrons over here, and they're going to merge together, and you're going to get the release of super fun chlorine gas. Okay, so a very unpleasant scenario, but what we're doing is we're pulling pure elements out of their compounds using an electrolytic cell. Okay, so in the history of humankind, this is a fairly modern method of extracting, useful elements. Okay, you might even consider this, I guess it's considered a form of smelting, if you want. Smelting is just the process of removing or I should say, elements from their ores. Okay, much more common thing you would see is the smelting of something like steel. That's very commonly done. Aluminum, steel doesn't use an electrolytic process. It uses heat and carbon to create steel, and I don't know exactly how that's done, to be honest. I wish I did, but I know aluminum is often extracted using electrolytic processes as well. So that's what electrolysis is, and you can do it to water actually. So you can take water, okay, and it has to have some electrolyte in it. And what you can do is you can actually invert water into two test tubes. It's quite easy to do. Has anyone ever done this before? Yeah. Yeah, right, because you can actually extract hydrogen. So what you do is you create your little, again, power supply here, and you'd have probes coming down in here. And actually, you don't need to do it this way. You can actually just loop them up and under, but whatever, it doesn't matter. And what will happen, as long as there's some electrolyte in the water, you'll get, remember that water actually kind of does this. So you'll end up with this happening over here, and actually you'll end up with just oxygen over here. I'm not sure the exact process, to be honest. But yeah, so you get oxygen ions coming in here, and they are reducing, or I should say oxidizing into O2, and you have hydrogen coming here, and it's reducing into H2. Okay, so I guess the overall reaction is this, really. I should just write out the reaction to make more sense. Okay, so you get that, and then this, and this. All right, and it's actually quite interesting. You're going to get twice as much hydrogen gas as you do oxygen. It's very obvious. So what'll happen is you'll get little bubbles here, and they'll start to displace the water. So you get like a gap up here of oxygen, and you'll get double that of hydrogen. And you can clean these tubes right out. Okay, eventually. Clean right out. Actually, what'll happen is once the hydrogen gets down here, it'll break the circuit and it'll stop, and you'll have this tube full of hydrogen and this half full of oxygen, and this does everything that hydrogen does. It pops when you put a flame in it and so on, and this makes a splint glow and so on. Okay.